Hello, so this, if I rotate the camera perfectly, good. So this is actually the last part of the video. I'm doing kind of bizarre time warping, perfect for a playlist about relativity. It's the magic of YouTube. I'm making this because when I got close to what now is the end of the video, I realised it had got quite long, and whilst I had initially wanted to cover everything, from classical material waves like waves of violin strings to Maxwell's equations, and then the derivation of the universality of the speed of light, doing all of that in one video would just make this video like 5 hours long or something, at least 4 hours, so I decided not to go down that path. Very important, whilst learning physics is amazing, you engage with, lots of areas of life, and, with it being summer, at least in England at the moment, you enjoy the sun too. So I'm keeping this video just to the first half, although I will touch on Maxwell's equations at the end. So in this video we'll look at the wave mechanics of waves on a violin string. We'll see kind of why waves form in violin strings, using a principle called the principle of least action, a very mysterious principle I'll explain more about shortly. We'll also look at how we can use sine and cosine functions, which are solutions to waves, for example, on violin strings, to build much more complex waves through Fourier series, and look at, for example, a square wave. Well, we'll talk about that anyway. We won't get into the maths of Fourier series, but we will mention that before we talk about why an understanding of the wave equation, which we will properly mathematically develop through the principle of least action, why an understanding of this equation is central to relativity, because we can use this wave equation to interpret deeply properties of electromagnetic waves predicted by Maxwell's equations. And there's one property in particular which is truly bizarre, which is the foundation of special relativity, and that's that the speed of a light for all observers seems to be constant, which is a totally absurd suggestion. I mean, for example, to me the camera, let's take an example of something much more ordinary than an electromagnetic wave. So the camera recording my YouTube videos. According to me, the camera is stationary. The way I make YouTube videos is perfectly consistent with assigning to the camera a velocity of 0. Otherwise, making YouTube videos would be incredibly complicated, and I'd have to do all kinds of tasks of continuously moving my laptop, and it would be a complete disaster. So, gratefully, I can define very legitimately the velocity of the camera to be 0. However, if there's an astronaut on the moon and he looks at Earth, he'll see the whole Earth moving very quickly. And that would include everything on the Earth. Well, you wouldn't see everything on the Earth, but if the Earth's moving very quickly, then according to the astronaut, everything on the Earth is moving very quickly, including me and the camera. So you see, if we shift perspective, then suddenly we go from the camera being, stationary in my perspective to the camera moving very quickly in the astronaut's perspective. And so velocity should be relative in that sense. It seems absurd to suggest that there should be something with absolute velocity, but that's exactly what Maxwell's equations predicted about electromagnetic waves, waves which carry electromagnetic energy associated with changing electric and magnetic fields. And the absoluteness of the speed of light baffled, well, it would baffle anyone, but out of that confusion was born special relativity. But all of that relies on an understanding of interpreting the equations, Maxwell's equations, and the equation for the electromagnetic wave particularly, and to interpret them we need an understanding of waves generally, which starts with much more familiar waves, waves with very much relative velocities, such as waves on violin strings. So this will be a journey of music, this will be a journey of waves, and this therefore will be a wonderful place to begin, a very technical but fun and hopefully joyful and enriching exploration of our cosmos through the wonderful lens of space-time and relativity. And on the next video we'll talk more detail about Maxwell's equations, though we'll mention it briefly at the end of this video. So I have done this slide before, but at that time I was planning to do the entire video going from violin strings to Maxwell's equations. So for an outline of the journey, I thought, not to mend the details of the journey we will take together, but to mend the distinction between what will be contained in this video and what will be coming up in, if you like, part 2. So in this video we're going to be doing parts 1 and parts 2. In the next video we'll be doing parts 3 and parts 4. So in part 1 and 2 we look at waves we are fairly familiar with. So I'm taking waves on violin strings because I love musical instruments. I would greatly encourage all of you to pick up a musical instrument. Now I can't play a violin to save my life, but I like tinkering on the keyboard, and there is a saying in physics which goes, to turn it into less technical kind of terminology, it essentially says studying physics is like learning about violin strings in ever increasing layers of abstraction, which is quite true. That is very much what physics is. In a sense, everything is a very abstract violin string, or kind of is kind of built from the mass of waves associated with, as we shall see, even violin strings. So to get an equation for a violin string when it's plucked, we ought to really start with, pretending we don't know it's going to form a wave, but maybe having some hunch it will. And so if we want to derive an equation for kind of a string, let's say under tension, which, is free to move along one axis, so, let's say bits of the string can move up and down, but the string can't slide from one place to another, then we need some method of kind of, once we have the model in place, finding some motion of our string, some description of the wave which will evolve over time and over the string. And a way we can get to such an equation is using Hamilton's principle of least action. Now, Hamilton's principle of least action is bizarrely global. It turns out for many systems, including even in the cases of general relativity, an object, or in the case of general relativity, even space-time itself, will have an action associated with it. And by minimizing that action, you can actually work out the equations of motion. In general relativity, those equations of motion are Einstein's field equations. For our classical violin string, though maybe in a future playlist we'll get to general relativity, but for our violin string it will be waves, material waves, which move through the violin string. Now, the idea of the action is related to Lagrangians. If you've seen Lagrangian mechanics before and digged into where the equations associated with Lagrangian mechanics come from, you probably have come across the action. But the fact that one can minimize the action and find equations of motion in such a wide array of things is bordering on disturbing with how universal it is, and I don't think it's really understood by physicists. I think most physicists would say that we don't really understand Hamilton's principle of least action. We can use it, we know how to use it, and we'll see an example of here, but we don't really understand where it comes from properly. We don't really, I don't think, understand fully what it's saying about how unified everything is in nature. But given how, exciting therefore the action is, but also how, as we'll see, relatively easily for such an abstract concept applicable it is to beginning our exploration into waves which will branch into special relativity, I thought Hamilton's principle of least action was the way to go. I have also mentioned it briefly in a video on quantum field theory, so worth talking about it here, but here we can actually do a proper calculation using the principle to predict something genuinely new rather than just using it as a kind of precursor to other equations which are more predictable directly in terms of computations in quantum field theory. And then once we've found the equation of motion on the string, which we'll see will allow for sinusoidal kind of motion, we'll generalize the equation of motion of waves on a string which is under tension to just a general discussion of waves which kind of transfer energy through matter. So that would include things like water waves. To get a general sense for how we describe waves classically, and then in the next video we'll look at Maxwell's equations, how they couple electric and magnetic fields, and seeing how with a bit of magic we can extract from them the idea of an electromagnetic wave and compare the equation for the electromagnetic wave with our generalized equation for how waves move through matter, more traditional waves, I should say, move through matter, to get some more information about some of those terms in the kind of equation for the electromagnetic wave, and therefore get to the heart of really the beginnings of relativity, the idea of the speed of light being a universal constant. So that is where we are going. Again, I do apologise if during this video I imply we will do 3 and 4. Due to time restraints we won't, but it will still be a very useful video. And if you like music, well, what better way to start relativity than to talk about, waves on musical instruments. Hello, so since we are going to focus on the principle of least action in this video, which is worth talking about how it works before we launch into using it to derive our funky equation for violin strings. So there are many ways we could actually go about trying to work out the equation of motion of a violin string or any one-dimensional object which is free to oscillate. However, one of the most fundamental ways of doing it is using Hamilton's principle of least action. Now, Hamilton's principle of least action sounds really fancy, and in some ways it is, but at its core it says we can describe, if we look at the dynamics of something, a quantity called the action, and each mathematical description of its hypothetical dynamics would have a particular value for the action associated with it. And we get this action, it turns out, by integrating the Lagrangian over time. So the Lagrangian tells you about the differences between kinetic and potential energy, and this magical quantity, which you can do a lot of stuff with, it turns out when you find the area underneath it, which would integrate the Lagrangian with respect to time, you end up with this even more magical quantity called the action. And it turns out a system, for reasons that became evident when we saw, ways of looking at quantum mechanics which may not have been immediately obvious. A system would like to minimise the value it has for its action. So there are many possible evolutions of a system we might hypothesize could occur, but a classical system will always pick the one which minimises the action. And the reason it does that is due to quantum mechanics, and there's a subtle clue in that the Lagrangian, being the difference in kinetic and potential energy, has units of energy, so joules, and since the action is the integral of the Lagrangian over time, it has units of joule seconds. But there's a very important quantity in the universe, a constant called Planck's constant, which also has similar units, indicating that the Planck's constant implies that the action has a lot to do with very fundamental things in quantum mechanics. Because Planck's constant, which has the same units, and so in some physical senses almost the same kind of thing as action. Planck's constant appears in Schrodinger's equation, it appears in wave-particle duality, it appears in Heisenberg's uncertainty principle. So action is something you see all over the place in physics. But to get to the action, we have to find the kinetic energy of our string, we have to find the potential energy, we have to take them away from each other. But because our string is a continuous object, we have to do a trick of considering the strings being made up of an infinite number of tiny, technically infinitesimal segments, where each segment is acting like a particle and therefore following very familiar rules about kinetic and potential energy defined for point particles. But using ideas in integration, we can add up the effects of all these individual, segments of the string, or the infinitesimal segments, to get the overall kinetic and potential energies, and thus to get the Lagrangian. And then we can integrate over time to get the action, and once we've got an expression for the action, we can see how this action changes if we alter if we alter the evolution of our string just a tiny bit. And the evolution of the string is given in terms of a function called y, which describes how at each point in the string there will be a displacement of the string from its natural position, and y also tells us how this displacement at a particular point will vary with time. And it tells us this for all points along the string, so y contains all the information we need to describe the wave and the motion of the string technically forever. So the action is going to end up through the Lagrangian to be a function of y, and by seeing how if we change y a tiny bit, s will change, we'll be able to get some expression for how sensitive our action s is. And it will turn out, according to our principle of least action, that the equation of motion of our string will be kind of any function y which will cause this variation in s to vanish. And this variation in s vanishes when s reaches a minimum value, because at the minimum value, the value of s can't drop any lower because s is at its minimum value. So this variation, this descent stops, and also at the minimum value, s hasn't begun ascending yet. So at the minimum value, the variation of s is 0. if you've done calculus before, it's like saying you've got a function, then at the minimum of that function, the gradient is 0. Very analogous. And we'll go through all of this in more detail, but this is our roadmap. So we have to find the kinetic and potential energy using ideas of infinitesimals and calculus. Then we'll be able to get to the Lagrangian and the action. Then we need to find how the action varies when we change y a little. And then setting that variation to 0, we'll end up with an equation in motion for y, which will therefore describe the possible kind of like shapes of our wave on a string, and even predict that the shape should correspond to waves in the first place. So that's where we're heading, and let's get cracking. So it's a lovely day, and I would encourage you to go for a walk in the park if it's still sunny near you. I've been for a nice walk, and now my head is clear. It's ready to do some maths, because doing maths is definitely better when your head is clear, and also when your stomach is not rumbling. A matter I shall sort out shortly. Not sort out shortly. Wordplay, I suppose. So we said that we needed to define the action in order to use Hamilton's principle of least action. But the action depends on the Lagrangian, and the Lagrangian in turn depends on kinetic and potential energy. So we need to get to the kinetic energy and the potential energy, which we'll come on to in the next part of this video, of our idealized string. However, before we can do anything like that, we have to model our string, because all physical predictions of the universe begin with some kind of model, often in some way idealized, but with a good justification. So it's also good practice to see how we can use that practice of modeling here to help us. Well, we'll start with something which is, fairly general for strings, including violin strings, because it just makes constructing a good violin so much easier if this is the case. We're going to assume that the density of the violin string is the same at all points on the violin string. Or in other words, we're going to assume the violin string has uniform density. Now, our string is idealized to be one-dimensional. That is, our string has a length, but it doesn't have cross-sectional area. Definitely doesn't have volume. So there's no point defining the density of the string to be mass per unit volume, because the string has no three-dimensional volume to speak of. Our string is idealized to just have a length. It's purely a one-dimensional object, and so if we're considering how the mass is distributed across the string, in other words, if we're considering the density of the string, it wouldn't make sense to go, well, density is mass over volume. No, instead we go, well, density is the whole mass of the string divided by the whole length of the string. So we're going to assume that the average density, the whole mass of the string divided by the whole length of the string, is not just an average density, it's the exact density, which is the same at all points along this string. And because we're talking about the density of a one-dimensional object, we use the Greek symbol mu. Now, you might be used to seeing the Greek symbol rho, which is like a curly P for density, but we use rho when we're talking about the density of a three-dimensional object. As we said, our string is one-dimensional, so its density is given by the Greek symbol mu, which is just equal to the mass of the string divided by the length of the string. As we're saying, mu has many meanings in physics. In maths, mu often refers to the mean of a statistical set of results. In physics, mu can also refer to the muon, a particle which is like a heavier version of the lepton, and a particle whose kind of detection on the Earth's surface in a fairly decent abundance is evidence of time dilation, which is a very important kind of piece of observational evidence for special relativity, which we will come on to in later videos. So we will use mu for muons in other videos, but for this video, mu just refers to the length. Sorry, mu just refers to the density of the string, so mu is just mass over length. So we've assumed our string has constant density. We're also now going to assume that the string, much like a violin string, is fixed at both ends. So one end is labelled x equals 0, the other is at the point x equals a. And we're free to have the x-axis rotated in any which way we want, because we invent axes in coordinate systems, so I'm just going to have the x-axis lying along kind of the length of the string. So the string is a units long, if you like, and the beginning of it is held in place, as is the end of the string. And because the string is held in place at both ends, and we've also said that the density of the string can't change, so the string can't in any places kind of like, if you like, compress or become longer. These two conditions together actually end up ensuring that the string, any point on the string, is not free to move along the x-axis, because moving along the x-axis, given that our endpoints are held in place, would mean altering in some region the density of the string away from this average value. And we've said our string always has uniform density, so we've in effect forbidden the string to move along the x-axis. But evidently our string is free to move, and it's very free to move along the vertical axis. So any point on the string can move up or down as it likes. And so we also define the displacement. So the displacement is how far the string has moved up or down, and it has the symbol y, because, motion up and down is traditionally associated with motion along the y-axis. Now a displacement y is a function of x and t, because the displacement of a point on a string will depend on where the point is on the string, and also how long this wave has been going for, and therefore what part of the wave cycle the wave is at that point at that time. So displacement is a function of x and t. And so now we come on to our first kind of mathematically tricky, if you like, bit of physics, which is how to calculate the kinetic energy of a string. And the challenge is that we're very familiar with calculating kinetic energy of point particles, that is, objects, and which we can at least kind of mathematically model as if they have no volume or size at all, and just exist at a single point in space. And indeed, if you were going to look far enough away from the string would appear like a point particle, but then you wouldn't be able to see any motion on the string, so it would be fairly redundant to ask what is the equation of motion of the string. So if we want to look at motion on the string, then we really need to consider the string truly as an extended object. But all the equations we have in physics initially, at least all the core central equations, are mostly for point particles, at least in classical mechanics. So how would we find, a value for something like the kinetic energy, say, for a continuous object like a string? Well, what we do is we borrow a trick from calculus. So, in calculus, there are many techniques where you can use the rules of physics for point particles, and using calculus methods extend these rules to talk about macroscopic objects. can do the same thing with our string. So in this kind of calculus-based approach, what we do is we consider our extended object, so in this case our string, as kind of being made up of many, many small pieces. And then we keep chopping these pieces into more and more segments. And then if we do this forever, then eventually, after eternity, each segment would have almost, it would essentially have no size. It would have what we call infinitesimal length, and the segment would be, therefore, a point particle, and it would behave according to the equations of point particles, because it has no kind of macroscopic or really physically meaningful extended lengths. Now, we don't say the length of this segment is 0, even though you might be tempted to do that, because the length of the whole string is clearly the sum of the length of these infinitesimal segments which make up the string. But if the length of the infinitesimal segments was 0, then we would have to conclude, well, the length of the whole string is 0, which would be nonsensical. So to get around this, we say that the length of these infinitesimal segments are infinitesimal. They're smaller than any number you can write down, but we don't treat them as being 0. So our string we can think of as being made up as infinitesimal segments, and each of these infinitesimal segments will act as point particles. So let's take one of these infinitesimal segments. Well, if we were to consider the kinetic energy of that segment specifically, we need, according to our formula for the kinetic energy of an infinitesimal segment of point particle, which is the kinetic energy is a half mv², to get the mass of this infinitesimal segment. Well, we said that the string has uniform density throughout, meaning, even though we've done something really bizarre to define an infinitesimal segment, the density there across the segment is still mu. So we've got the density of kind of mass contained in the segment as mu, and we defined the density to be mass per unit length, and therefore the mass of the segment is just the density mu times the length of the segment. Now, because this is kind of an infinitesimal segment, essentially we've really just zoomed in almost an infinite amount to be able to see this. This segment looks flat because any kind of like curvature or even kind of like diagonal nature of the string over such a tiny region seems kind of negligible. Because the wave is smooth enough that, when we look at infinitesimal segment, it appears, because we've zoomed into the string so much, almost perfectly flat. So the segment lies only along the x-axis, and so its length is across the x-axis, and so we say it has an infinitesimal length across the x-axis, which we call dx. And so the mass of our infinitesimal segment of our string is just mu times dx. It's mass density times the length. So we have the infinitesimal mass. Well, you might now ask, what's the velocity of this infinitesimal segment? Well, we said that the string can't move, including this infinitesimal segment, horizontally. It can't move along the x-axis. What it can do, however, is move freely within reason along the y-axis. It can move up and down, and therefore all of its velocity is going to be vertical velocity, which is going to be the change in y over the change in time. Or, kind of in the language of calculus, it's the partial derivative of the y coordinate, so it's displacement with respect to time. And we have to square this kind of derivative to get the velocity squared, to put in our expression for the infinitesimal kinetic energy of our infinitesimal segments of the string. And then once we have the infinitesimal kinetic energy, we just sum over the kinetic energy of all these infinitesimal segments to get the total energy within our string as a whole. And because we're summing over an infinitesimal, all infinitesimal segments, we're doing a very special kind of sum because we're summing an infinite number of things, each with an infinitely small contribution. And this summation is so special it has a special name. It's called integration. So we say we integrate over the kinetic energy of the infinitesimal segments to get the kinetic energy of the string as a whole, leading us to this beautiful equation for the kinetic energy. So we've got half times the mass, which is mu dx, times the velocity squared, where the velocity is the rate of change of y with respect to t, and then we integrate from the start of our string, which is at x equals 0, to the end of our string, which is x equals a, to get the total kinetic energy in our whole string. Now you might notice here I put the x in the middle of this term after the integral sign. That's because I wanted to show you where this comes from. However, because when we evaluate integrals, we think of this infinitesimal as telling us what we're integrating with respect to, we often put it at the end. So it looks like we're integrating something with respect to, in our case, x. However, in terms of seeing where this infinitesimal actually comes from, I think it's a lot better to sandwich it in the middle. So we now have the kinetic energy of the string. To get the Lagrangian, we now need to get the potential energy. But we could use a very similar technique in terms of treating the string as being made up of infinitesimal elements. And we're also going to make very good use of the idea that the string, because it's a physically real string, is never going to have a point on the string which has infinite displacement. All points on the string might rise or fall across various points in time, but they're never going to shoot off to infinity. As all violin players can attest, and we're going to make very special use of that very core idea when we talk about using the calculus-based approach to find the potential energy of the entire string as a whole, such that we can eventually get to the Lagrangian. Hello, so now the sun has indeed began descending, and I was going to turn the lights on, but actually this is kind of somewhat atmospheric, the atmosphere of this. So for this slide, let's kind of run with it. And by next slide I might need to change location anyway. But before we looked at the kinetic energy of our string, now we'll look at the potential energy. And again, we are modelling our string as a one-dimensional string of uniform density with fixed ends. And we also are considering it mathematically as essentially being composed of an infinite number of infinitesimal segments. So, if we're considering the potential energy of the string, really far removed from any of our modelling of the string, we have to firstly think about what potential energy is. Well, potential energy is energy that a force is causing to be stored in something. So energy which can be released and quickly often converted into kinetic energy when that force is removed. So, like if you're, for example, lifting an apple we're doing work against gravity, and although you can't really remove the force of gravity, you can remove the force that you're, in terms of remove the force holding the apple to your hand by just opening your palm. The apple will fall, and the gravitational potential energy it's gained as you lifted it will be converted into kinetic. And it's potential energy because as you're giving the apple the potential energy, the apple isn't, vibrating, it's not suddenly growing very hot or anything, it's kind of storing this energy which it can release the moment you let the apple go. So that's what potential energy is. Now in our string, the thing that is giving any infinitesimal segment potential energy will be the tension present at that point in the string. So the potential energy is a result of the tension, and therefore when we're calculating the potential energy of a particular segment, we need to calculate it based on the tension that segment is under. And to get the energy associated with that tension, what we can do is we can multiply the tension at that place on the string by the by, if you like, the vertical display, by, if you like, the changing length caused by the vertical displacement of this infinitesimal segment, which the tension has resulted in. And it's this kind of like change in the length. And because it's an infinitesimal change in length, this doesn't, violate our idea of kind of the density of the string being preserved across it. Because it's only an infinitesimal change in length. But that infinitesimal change in length kind of causes there to be tension in that part of the string. Now, for the tension not to kind of cause the string to sail off into infinity at some region, the tension has to result in a macroscopic segment of the string, which might, all be kind of climbing up to some maximum displacement or going up to some kind of amplitude, to have overall a finite maximum displacement. That is what we want, a finite amplitude for our string. But if we look at a segment, let's say, a quarter of the wave cycle on our string, then that segment might, each point as we go along the x-axis in that segment, the string might be increasing in displacement more and more up to some maximum amplitude. And because this kind of quarter of the wave cycle on the string, so like a quarter of the wavelength, is a macroscopic distance, it's not an infinitesimal distance, that means that there is an infinite number of infinitesimal segments within even that part of the string. All of which are contributing to the, if you like, total amplitude of the string, because the displacement is going up and up and up. So if the tension was resulting in each infinitesimal segment within that bit gaining a macroscopic increase in vertical length, then because we have an infinitesimal number of segments we need to sum over, the net result would be we would have an infinite amplitude. Our string would have to go off to infinity, but clearly that's unphysical. And so to prevent there being an infinite amplitude, we need the displacement that the tension on the string causes for each infinitesimal segment to be itself an infinitesimal increase in length. or an infinitesimal push upwards, if you like, in the y-axis. And so, crucially, the increasing length we're talking about for an infinitesimal segment is itself infinitesimal, and because we said, well, of kind of string is free to move along the y-axis only, the additional kind of length of that segment can only be due to a movement upwards in the y-axis. So we say has, if you like, essentially, gone from having a kind of thick, well, I say thickness, meaning length dx along the x-axis, to having a length dx along the x-axis, but also dy along the y-axis. So in other words, due to the tension, our infinitesimal segment is now kind of diagonal and forms kind of the hypotenuse of a right-angled triangle, with one side of the triangle being its horizontal length dx, the other being its vertical length dy. And we know how to calculate, using Pythagoras' theorem, the length of this, the new length of this infinitesimal diagonal segment. We just use Pythagoras' theorem. And this new length will, by Pythagoras' theorem, be the square root of the horizontal length dx, and I've got to square that, so dx squared, plus the square of the vertical length, so plus dy squared. But then to get the change in length, so how much the segment has increased in length from its original length, we have to subtract this new length away from the original length, which is just dx. So the change in length of the infinitesimal segment due to the tension is just the square root of dx squared plus dy squared, and then minus outside of the square root dx. Now, because dx and dy are by definition incredibly tiny, we can use many approximation methods. One I might suggest is, with a bit of playing around with this expression, you can use the binomial theorem, and you'll quickly and fairly easily find that the changing length to a very good approximation is just half times dx, that's the original length, and then multiplied by the gradient, if you like, or the steepness of the infinitesimal segment, so partial derivative of y with respect to x squared. So we now have a formula for the change in the length of the string, and the energy transferred, which in this case is potential energy of a force, is just the force, which in our case is the tension, multiplied by this kind of like, if you like, changing length of the string. So we we now essentially, and we can use tension times changing length without worrying about the tension varying, because the segment is infinitesimal. It literally has practically no size for the tension to vary across, so we can consider the tension T across this infinitesimal segment to be a constant. So we now have a formula for the potential energy of the infinitesimal segment, which is just T times our expression for the changing length of the infinitesimal segment, and we integrate over the number of infinitesimal segments to get the total potential energy present in our spring, which looks something like this beautiful formula here. So now we have an equation for the kinetic energy, we have an equation for the potential energy, and we can bring it together to find an equation for the Lagrangian. So we have now got an expression for the kinetic and potential energy, and putting them together we can define the Lagrangian, and we can combine them into a single integral over x, because both the kinetic and potential energy was integrals individually over x. And the way we compute an integral, we can, re-split the integral up into two terms if we really wanted, into two integrals if we wished. But we can write the whole Lagrangian as a single integral, where we're integrating over our distance x. And our Lagrangian, based on the expressions we have for kinetic and potential energy, and the fact that the Lagrangian is by definition the kinetic minus the potential energy, the Lagrangian will look like this. And now we can define the action for our string. Finally we can get to the action, and then we'll minimise it to find the equations of motion of our string, or in other words, how the shape of the displacement of the string at each point changes with time, or in other words, finding an equation of motion for y of x and t. So we have our Lagrangian, and to get our action from it, we integrate the Lagrangian over time, and we end up with now a double integral. We call it this a nested double integral because the first integral is kind of contained within the out integral. Now, because x and t are kind of going to be independent, because we're not worrying about relativity yet, so we don't have to worry about x and t having any interdependence on each other. The order in which you integrate this really doesn't matter. You could have your x as your inner integral and your t as your outer integral, or your t as your inner integral and x as your outer integral. We really don't care. But the important thing really is x, because we're integrating over the distance x of the string, and the string is of finite length and goes from x0 to xa. X will go from 0 to a, so 0 is our lower limit of our x integral, and a is our upper limit of our x integral. And we can also place limits, if we wish, on the time integral. Now, I think it's very natural to start counting time from t equals 0, so I've chosen 0 to be my lower limit of time. And you might wonder, well, what would a suitable upper limit be? Well, because, as it turns out, our string will allow, in fact require, kind of like periodic behaviour, t, it could be said to have some, reasonably argued finite upper, well, time could be considered to have some reasonably, argued finite upper bound, that we really care about. However, you can, if you want, just define the action of the string to be the integral of the Lagrangian from t equals 0 all the way to t equals infinity. So it's worth saying I put t as the upper limit for my integral of time, but it doesn't really matter what t is. So if you're unsure what t is, don't worry, it really doesn't matter. It doesn't matter if it's finite, it doesn't matter if it's infinite. The important thing, however, is that we are integrating from one time to another. So I've said from time 0 to time t. So we have our action, but you might remember Hamilton's principle of least action, as the clue is in the name, tells us what we want to do is to minimise the action. Therefore we need some description of how the action can change. We don't actually want the action itself, and this might fill you initially with dread. So when we say how the action changes, we're talking about a variational derivative, not an ordinary derivative. And that's because the action is not a function. Because a function is a mathematical object that takes in a number and gives you back another number. For example, a function is like y equals x squared. If I give it x is 1, it outputs y is 1. If I give it x is 2, it outputs y is 4. So I give it an input, it gives me an output, both of which are numbers. However, the action isn't like this. The action takes the entire function y of x and t, that is the entire description of the shape of the wave at every point on the string across all of time, essentially, if we have an infinite upper bound for time. And it takes all of that to give you an output value for the value of the action s, associated with that kind of motion of the string. So the action is an object that takes in a whole function and outputs a number. It doesn't take in a number and output a number. And because it's taking in a whole function instead of taking in a single number, we call it a functional. And you might wonder, how on earth do we vary a functional? Or how do we find the variational derivative of a functional? And particularly with the expression looking so bulky, you might feel like either going to the tops of Everest to never see calculus again in your life, or maybe even descending to the deepest circles of hell to have an audience with Lucifer to encourage him to demand God to alter the laws of physics, so physicists are not faced with such daunting looking expressions for the action of something so seemingly simple and benign as a one-dimensional string of uniform density, the simplest continuous object we can possibly think of. However, dread not, because whilst we are minimizing a functional, we are still minimizing something that depends on an input. And so many things about how you would minimize a function, which is also about considering how a function changes with an input, or the output of a function changes with an input, can be applied here. We just have to take into account that for a functional, the input is a whole function, not a number, but lots of the same principles as to how you would minimize a function or find the minimum of a function can be applied to our action over here. So, if we want to minimise, let's go back to a nice ordinary function like y equals x squared. And when I say minimise, what I really mean is find the value of the input for which the output has its minimum value. So we want to find like the minimum point of, if you like, the curve y equals x squared to just get us started. Well, at the minimum value, because it's the minimum value, the function can't keep descending at that point, but also because it's the minimum value, the function can't have already begun ascending. So at the minimum value, the function is neither ascending or descending, it's essentially flat, and if we zoomed in really, really closely into the function around the minimum value, we would indeed see that the function does appear to be flat. Or to put another way, we would see that kind of like, if we zoomed in really closely, when we changed the x value an infinitesimal amount, the y value didn't change. So the infinitesimal change in the output, so for a function, the y value divided by an infinitesimal change in the input value, so for a function x, would equal 0. Or in other words, we say the derivative of y with respect to x is 0. Now we can do a very similar thing with our function on here. We can kind of consider the kind of function as a curve, but each point on that curve now has as one of its coordinates not a number, but a whole function, because kind of its coordinates given by the output and the input, and the output is a number. The action, once you give it a function, will be a particular number, but the input is an entire function. But still, we have the action giving an output when you give it an input. And we could consider, well, if we change the input a little bit, how does the action change? And then we can think about finding a input for which there is no change in the action at all if the change to the input is infinitesimal. It's just with functionals, like when we're calculating actions, the input is an entire function, but it still works very much the same way. And so we can kind of define, if you like, a change in a tiny change in an input, and we use the symbol kind of a delta, lowercase delta for a tiny change. So if we're changing the input a little, we're shifting our function y of x and t into a kind of y of x and t plus some infinitesimal change. And just as when you're doing standard calculus with functions, you don't really care about the details of the tiny change dx you're making along the curve. You just care that it's an infinitesimal change. The same thing when we're trying to minimise functionals. We don't care about the details of exactly what this infinitesimal change to the input looks like. We just care it's an infinitesimal change. So if you're looking at y of x and t goes into y of x and t plus delta y of x and t, and you're like, well, what is delta y of x and t? It's just an infinitesimal change in y, and rest assured that will be all we need. So we now have kind of like defined a tiny change in the input in y, and then so if we look at what the action is like when we've changed the input by this tiny amount, we can subtract this new value of the action from the value of the action where the input was just y, and we end up with an expression for how the action changes. And it'd be infinitesimal change in the action because we're looking at how the action changes when we change the input, which in our case is y, infinitesimally. And if you go through that process, just using our expression for the new value of y, the new value of the input, the original value of the input, and the expression of our action, you can easily verify for yourself that the change in the action when you shift the input y a tiny bit will be given by this expression, which looks confusing. I know it looks confusing, but it can be worked out by just brute force, which I would encourage you to do. And hopefully I've given enough here to help you do this. And if you prefer not to, you're more than welcome, obviously, to take me on pure trust. But we have an expression now, finally, for the change in the action when we change the input an infinitesimal amount. And you might realise when I wrote the change in the action I've been slightly sloppy. Instead of writing y of x and t, I just wrote y, because by this point we know y is a function of x and t, so there's no point writing what y is a function of explicitly anymore. So we have an expression for how the action changes. Now the question is, well, how can we minimise this? So we'll be going on to looking at that in a couple of slides' time, but because I know the idea of a functional is fairly abstract, in the next slide I've just got a bit of a graphical illustration taken from one of my earlier videos where I briefly talked about all this variational derivative stuff, to help kind of clarify a visual picture of what a functional is and help solidify the comparisons between variational derivatives, which essentially look at how functionals change, to ordinary derivatives, or dash partial derivatives, which look at how traditional functions change. So that's coming up, but we'll be making use of this infinitesimal change in the action in a bit, although we'll have to do some mathematical jiggery with it. As it is, we've just used brute force to get there, but to help us work out how to minimise it, we have to be a bit sneaky with our maths, but we'll come on to that in a couple of slides' time. So, we mentioned that we're going to look briefly visually at the distinction between a function and a function. So as we said, a function is something like, for example, y equals x squared, where x could be any real number and y could be any real number. So if x and y are real numbers, it's just once you pick an input, let's say x, which is a real number, you will get a specific real number, y, as an output. Given by the rule, the value of y is equal to the value of your input, which is x squared. For example, if you give the function y equals x squared, x is 1, it will return y is 1. If you give it x is 2, it will return y is 4, so on and so forth. And you can come up with lots of exotic functions. You can even draw functions which we might not have analytical expressions for, like the very squiggly function I've drawn here. As you can tell, I'm not an amazing artist. I love art, but my drawing skills have never matched my enthusiasm, and my portrait creations are disastrous, to say the least. So the squiggles is actually rather excellent art by my standards, by my own kind of artistic abilities. But we have a function, and we can clearly see that this function has places where it reaches a minimum. And if it was perfectly smooth, it would be even clearer to see that at the minimum, the function has stopped descending, and after the minimum, it will start ascending. And therefore, the minimum corresponds to a point of zero gradient. And this is exactly analogous to what looks like around the minimum of a functional. It's just with a functional, which is kind of some function of functions, if you like. That is, it almost behaves like a normal function, but where the input is at x, the input is the whole function itself. So sometimes a functional is written as a function with a function input. But a functional, like a function, outputs a number, but as I say, the input is an entire function. And we can represent a functional as a curve, but now it's a curve where each point in that curve has as one coordinate, like normal, the output number, but as its second coordinate, now an entire function, not just a number as an input. So we can think of functionals still graphically, we just have to bear that detail in mind, but the same principle applies to how you would find the minimum of a functional. However, as you're varying the input function, not an input number, it makes sense to have a different name for how we find the minimum of a functional. Thus we call it taking the variational derivative of the functional and setting that derivative to zero. Indirect analogy to how we take the ordinary derivative of, let's say, a function f of x and set that to 0 to find the places x where our function f has its minimum value. So that was just a quick crash course on functionals and functions. Now with that graphical underpinning, let's return back to our expression for the infinitesimal change in the action. associated with our one-dimensional uniform string. Then we'll do a bit of maths to help us find how to minimise it, and that will lead immediately to an equation of motion. Those of you who have done lots of wave mechanics before will be all too familiar with. Hello, so I've changed location, nice bright room, lovely bright paint, a little dark outside but perfectly peaceful for some lovely maths. So we've talked about the functional, we talked about the analogies between variational derivatives and ordinary derivatives, and we've said how we can to a degree at least graphically think about minimising the value of an action. Well, I mean the value of a functional, but for our purposes the action, by considering what happens when you change the input, which for our purposes is the displacement function y of x and t, a tiny bit. And we ended up with a explicit, if slightly unwieldy, expression for our changing the action, our infinitesimal changing the action, delta s, and this was the expression we had. Now, as we said, we really want, if we're going to find a minimum value for the action, or at least a stationary action, we want this change in the action to become zero. We want the infinitesimal change to just vanish, or at least to vanish in the limit where our infinitesimal change in y goes to zero. Or in other words, where our change in y becomes infinitesimal, really. And you might think, well, one way to do this is just, well, to set the terms in the brackets, set the terms together as saying, well, you know, both of them together combined will equal zero. That way, the change in the action delta s will equal the integral, the double integral, I should say, of zero. But zero, when integrated any number of times, will give you zero, so you'll end up with the variation of the action is zero. And you might think, well, that's exactly what we want, and then we'll have a wonderful equation of motion. The problem is, with that equation of motion, the equation of motion will be explicitly including delta y, our infinitesimal change in our kind of input function. But we don't want a final equation in physics to refer to infinitesimals of anything, because it's not clear whether it's logically even coherent to talk about something in a literal sense, in reality, changing an infinitesimal amount. We can talk about it abstractly and have it have these infinitesimals as kind of terms present in intermediate calculations, but we can't have a final equation describing some physical process, some physical motion, some physical evolution, where infinitesimals roam free. But we really want these infinitesimals to ultimately go away. Now, you might have some hope, because we have, there's a slight annoying thing that we're taking derivatives of our infinitesimals, but we are integrating. And maybe the integration will cancel out the derivatives, and it will all, and then we'll be able to do some magic, and it will all end out lovely, and we'll have an equation without infinitesimals. Well, that's actually almost what we need to do. The thing is, if we try to evaluate it explicitly in this form, by which I mean carry out the integration, we would be left with a very problematic term. Because, after our minus sign, we've got t and then we've got partial derivative y with respect to x, but then we've also got a partial derivative of delta y with respect to x. And even if we used the integration over x to get rid of that partial derivative, we would then be trying to integrate delta y over time. And it'd be very hard to know what to do about that delta y. It turns out the infinitesimal being differentiated on the kind of first term, so where we have the infinitesimal being differentiated with respect to time, is not nearly problematic. Not nearly as problematic, and that's for reasons I will come on to in a bit. But first we do want to do something to get rid of this partial derivative of delta y by delta x. Sorry, I mean the partial derivative of delta y by x. So we want to get rid of that term if at all possible, and we can do that through using the product rule kind of in reverse, because if you take this rather ghastly, I appreciate, but if you take this bottom equation here, apply the product rule, you'll see you'll end up with the top equation, but beautifully this equation will not result in us having to worry about integrating delta y over time, because that pesky term in the top equation of the derivative of delta y in terms of x has just kind of like vanished. And you might wonder, well, okay, well that term is gone, but how do we go from here? Well, you can, being fairly free with the order of the integrals, you can evaluate this. And when you evaluate it, you'll have a beautiful thing where all the annoying partial derivatives in terms of time go away because you're integrating over time, leaving you with a situation where you're essentially trying to evaluate integrals over x. And that includes considering delta y when x is a and delta y when x is 0. But our boundary conditions now come in and do something rather magical. So it's worth recalling that the points x is 0 and x is a are very special. They represent the end points of our string. And the special thing about the endpoints is we said at the beginning, when we were developing the Lagrangian such that we could find the action and then eventually the infinitesimal change in the action, we said at the beginning that the endpoints are fixed, they cannot move. And what that means is no matter what physically possible change delta y we apply to our kind of equation of motion, the endpoints will remain fixed. And so this delta y, this shift in the displacement of the string at the endpoints, and only at the endpoints, can be guaranteed to be 0. We've defined this to be true at the very beginning. And what that means is terms, after you've evaluated the integral in the bottom expression, that terms will just start to just vanish, at least a couple of them, and then you'll end up with a beautiful equation of motion, which you guessed it, it's a wave equation. So I wrote it firstly in the way you'll probably end up getting to it at first, when trying to follow this process to to get delta S equal to 0. But then I rearranged it in something more useful below. So these two equations, given also our boundary conditions, will assure that delta S is 0. And so we have now finally succeeded in getting an equation of motion for a one-dimensional string. It's worth saying there's been a lot. We talked about functional derivatives, variational derivatives. There are also something called functional derivatives. We've looked at some rather hideous equations, but we've ended up with two really beautiful equations. And if we look at these equations, they tell us something very interesting. They tell us that any valid solution to the motion of the string, that is any valid function y of x and t, which satisfies these two partial derivative equations and therefore will, by virtue of that, minimize the action S. All these possible solutions y are solutions where the second derivative of y with respect to x is some, constant times the second derivative of y with respect to t, and that indicates some symmetry about space and time, which often gives rise to kind of periodic behaviour, and that's why you have periodic motion in the string. And also, if we think about possible functions, more explicit functions that might satisfy this wave equation, well, if we think about it, the easy kind of functions which might satisfy this are functions where when we differentiate them twice with respect to a particular variable, input variable, we will get back that same type of function, because that will make satisfying this equality between second order space and time derivatives very straightforward. And functions which do this, functions which when you differentiate them twice you get back the same function, might be known to you, because examples of functions that do this are the sine and cosine from trigonometry, and you might recall that these functions have the shapes of waves. Thus we already see that we should expect some kind of wave behaviour on strings. However, it's worth saying we've talked so far very exclusively about waves on strings, but how would we generalise this to, say, waves on the surface of water, or more generally, waves going through materials, and that's what we'll look at in the next bit of this video. So, we start with our kind of wave equation from the earlier slide. And you'll notice that this kind of scale factor, this proportionality constant, if you like, which relates partial derivatives of y in terms of x with partial derivatives of y in terms of t, it's, if you like, a ratio between two important constants in our string. So firstly, the tension the string is under, and also the density of the string. However, whilst this is great for one-dimensional strings, it's not very good if we want to generalise this equation to have this scale factor written so explicitly in terms of values which are designed for one-dimensional strings. For example, if we have, waves on the surface of an ocean, then considering density as a mass per unit length isn't very natural anymore, because these are waves on the surface of water, so mass per unit area would be a better measure of density. And also, it's not very clear what the tension would be, or what exactly we would mean by the tension in the water wave. So we want to look at a ratio, this ratio we have and see whether it's corresponding to anything more general about waves, which might allow us to have a general wave equation. Well, one thing you should always do if you don't know what the ratio between two quantities physically refer to is check the units of the two quantities, do a bit of algebra, and find out what units the ratio of those quantities would have, and that would tell you what physical thing that ratio might refer to. So if you look at the units, and generally in physics we're talking about the units of a quantity with square brackets around the quantity, of our mass density and our tension, and note that, the mass density has units of kilograms per meter, and the tension has units of newtons, or if we use Newton's laws, that would be equivalent to kilograms multiplied by meters per second squared. Then, if we do the mass density divided by the tension, we'll end up with something of units of essentially meters to the minus 2 multiplied by second squared. Or in other words, we'll end up with something with the inverse units of velocity squared. So we can rewrite the wave equation as our kind of bottom equation in the blue box here, where now we have rope velocity. So for a kind of wave on a one-dimensional string, the velocity would be given in terms of, could be calculated in terms of mass density and tension, but our bottom equation in the blue box is quite general, because all waves will have some velocity, because all waves have some kind of motion, they propagate in a particular direction, and so this bottom equation contains all we need to understand wave behaviour of waves through materials, and it will turn out also contains the seeds to understand electromagnetic waves, even though these waves do not travel through materials, bizarrely. So we now have the most general classical wave equation we can have for at least material waves, although it bears lots of resemblance to electromagnetic waves too, as we will see. And it contains both implications about periodicity in terms of relating derivatives in space to derivatives in time, which would imply periodic functions like sine and cosine to be solutions, but it also now contains as kind of something that relates these second derivatives, the velocity of the wave. And so now we will look at kind of like sine and kind of cosine curves, seeing how we can think of solutions just generally as really cosine curves with different phases, and then we'll see how we can build up much more, strange waves like square waves from sine and cosine, thus concluding our discussion on material waves. So I mentioned that possible solutions are sines and cosines, but we can kind of merge them all together as just kind of thinking of cosine solutions of different phases. And we can do that using double angle formulae from trigonometry in a mathematical way of thinking about it. But physically, really, the sine function is just the cosine function just shifted along. So if we take the cosine function and just shift where at each point the input, the wave is at in terms of its cycle, then we'll end up with the sine function. So the sine function and cosine function are essentially the same thing, just one is displaced from the other, and we can see if we look at this kind of these curves, where, here x is essentially, given in, if you like, radians. So this isn't using degrees. This is using radians, where 2 pi radians is equivalent to 360 degrees. So if we look, for example, at our orange curve, well, we can see when x is 0, the orange curve is at 0 displacement, but then when x is what would be kind of roughly, 1.5 or something like that, essentially something like pi by 2, which will correspond to, 90 degrees, the output is 1, and we see that this is following the pattern of a sine curve, but you can see we can represent the sine curve as just a cosine curve, but a cosine curve of x minus pi by 2. So we can get a sine curve by just shifting the cosine curve along by pi by 2 radians, or if you like degrees, by 90 degrees. And if you wanted to, you could easily substitute y equals cos of kx minus omega t into the differential equation we had for a wave, and you'd be able to verify that this equation would satisfy everything, providing k related to the wavelength of the wave in a particular way, so how spread it out is in space, and omega related in a very particular way to the angular frequency of the wave, so how long it takes the wave to repeat itself. But these are general solutions. And you see, I've got the cos curve in blue, but I've also got a curve which isn't really the sine curve or the cos curve, because I've just shifted the cos by, not 90 degrees, but by 180 degrees, or in other words, pi radians. But all of these have traditional wave shapes, and you can verify for yourself easily all of them will satisfy the general wave equation we had on the previous slide. So now we're going to talk very briefly about how we can use sine and cosine waves to build very strange waves, and that will lead to a discussion of really a more complete understanding of waves on a violin string, and why you get some very strange patterns when you let the string go, if you take into account things like damping and energy loss. And that will conclude everything we need in terms of solidly understanding waves through physical matter. So here I've got, for comparison, a sine wave, which, as we saw before, we can write in terms of cosine waves, and then I've got another wave, another strange wave that looks like it's almost approximating a square wave, kind of like a square which regularly just flips over, kind of periodically. And this strange orange kind of approximation to a square wave is very much an approximation to a square wave, and you can actually construct it using sine and cosine, or based on what we said before, essentially just cosine waves, by adding cosine or sine waves, if you like, of different amplitude to each other, to build this very unusual wave. And I think in my code I only added about 3 different waves of different amplitudes, and we've already got something that looks a lot like a square wave. If you added an infinite number of the correct waves with the correct phase shifts and the correct amplitudes, you would get exactly a square wave of the height you desired. And it turns out that actually any periodic pattern can be described as sums of sine and cosine functions. So anything that is periodic is essentially a bunch of sine and cosine functions. But a bunch of sine and cosine functions with each one having a different amplitude. And because the amount of kind of damping on a violin string a wave will experience depends heavily on the amplitude associated with that wave, what that means is over time, if you start with a very, strange initial condition on your wave, on a violin string, you'll get the amplitudes of the waves which make up this very strange initial shape decaying but not at equal rates, leading to ever new mixtures of sine and cosine waves, leading to new shapes of waves, well, overall waves seemingly forming. And so you can use the idea of breaking a very complicated or strange wave into sine and cosine to actually model how the wave will evolve once damping takes place. And you can get some rather cool animations which do look very real because it very accurately describes what happens. And the kind of maths you use to work out what sine and cosine functions to add together to build or to model a particular strange looking wave. The maths to do this is called Fourier analysis. You use Fourier series, which are your series of sine and cosine functions. So Fourier series essentially allows us to describe all periodic waves in terms of sine and cosine waves, and each sine and cosine wave will, as we said, obey the wave equation we had derived using the principle of least action. So the principle of least action, as well as describing very simple waves, describes a very complicated wave evolution when we're considering damping. If we, bring the powers of Fourier analysis to our aid. So this video has been mainly about waves travelling through matter. However, we ended up with an equation that simply describes something periodic with wave-like properties in terms of periodicity and related partial derivatives to a velocity. Now, usually with matter waves, we might use kind of constants, let's say for a string, the tension of the string, and the matter density to work out the velocity. But let's say we had an equations or bunch of equations that tells us the derivatives of some kind of displacement y, and we wanted to work out the velocity that a wave obeying those equations concerning the derivatives would have. And it turns out Maxwell's equations provide the derivatives of fields, and so using them we can actually work out what velocity waves associated with these fields, this electromagnetic field, should be. And it's this idea that leads to an understanding for the universality of the speed of light and the speed of light as a constant in nature. So I know this video has been quite long, but I thought as we're doing a playlist on relativity, it is important to build it, starting from things we are familiar with, because it is going to get very strange and very abstract indeed. And also, music is at the heart of everything because it's ultimately the wave equation which allows us to get to the constancy of the speed of light, which in turn leads to all the bizarre effects of relativity. from time dilation to muons living far longer than they should, to mercury being a liquid at room temperature, to particles when we also take into account quantum mechanics and having spin and electrons despite having negative charge liking to pair up in orbitals of atoms. There's so much we get from ultimately considering waves. And waves ultimately come from a principle, Hamilton's principle of least action. I think we are just beginning to understand. So I hope you like this, well, I hope you found this video fun. I apologise for it being a little long, so much to cover, but we'll get on to Maxwell's equations next time, and also introduce towards the end of that video the reason why we define space-time and define something called a space-time interval. And that will lead us then on the oncoming video to talk about, well, oncoming video after that, to mention 4 vectors, and then we'll look at the geometry that these 4 vectors indicate about space-time, where we'll be talking about kind of hyperbolic geometry, which will lead us eventually to the Lorentz transformation matrix and a discussion of time dilation and all the wacky effects of relativity, ultimately coming from knowledge of both electromagnetic phenomena and, well, violin strings. You know, the world is essentially a very abstract violin.